I actually had the privilege of going to a real DevSecOps talk this morning. And about halfway through that talk, I said, oh crap, I got to rewrite my slides. Because I realized that I'm not really doing DevSecOps. I'm doing DevOps with an offensive twist and perverting a CICD pipeline for fun and profit. So I changed the title slide to reflect this. By the way, I'm Joff. Some of you may have noticed that we have a Discord channel within which we use to engage the community. It turns out that the participants in the Discord channel have some real game when it comes to memes. Okay? And all sorts of strange things appear in that channel from time to time. So I try to stay alert and I capture them as best I can. And I actually do have a handle on GitHub called Yoda, which obviously somebody picked up on. And that one is hysterical. Well, I think so. About me, I am working at Black Hills Information Security. I am an anti-siphon instructor. For those of you that did anti-siphon courses this week, thank you for supporting the cause. We really are trying to bring quality instruction to you at an affordable price. That's what it's all about, okay? I have the unofficial title of Malware Pit Boss. I made that title up. I have a couple of devs that work for me now, and we create interesting things. First of all, there's this thing, DevSecOps, and then there's this other thing called SecDevOps. And I'm Googling around, I'm going, this is a thing? Why is the sec there and not there? I don't get it. Right, but then I had the realization this morning I'm not doing either anyway, so it doesn't really matter anymore. So, Jedi mind hack, this talk is not really about securing malware. If you think about DevSecOps, a lot of it involves security tests and QA tests in a CICD pipeline to produce better quality software. I'm producing malware. I would like to have high reliability, but the quality I could give a, well, you know, right? Let's talk about malware for a minute. The defense landscape has become difficult. Who out there does pen testing, internal pen tests in Active Directory environments and red teaming, right? Probably a bunch of you. You're up against this now. EDRs and XDRs with static artifact analysis, event tracing for Windows, Windows kernel mode callbacks, Windows DLL API hooking, process tree analysis, memory page scanning, call stack tracing and analysis, and kernel driver block lists in Windows 11. What the heck happened? Some people got their act together is what happened. Remember the good old days of hacking? Hey, I get Metasploit. Yeah, I'm talking 10 years ago now. I grab Metasploit, I fire off a exploit. It works the first time. And I jump up and go, ooh, I'm DA, awesome. It doesn't work that way anymore. So what are these things? Static artifact analysis. Well, direct malware hash match in VirusTotal and Friends is one way that we get a static artifact analysis. Unencrypt shellcode byte sequences and patterns in malware artifact samples. High entropy of a binary artifact. Any little telltale thing in an artifact that will trip off, or trip, should I say, any defensive product to say, that's bad, right? An entropy score of a binary artifact above, anything above about 5, immediately malicious. Okay. Event tracing for Windows. Boy, this stuff is fun, and it's good technology, right? I got to hand it to Microsoft. This was well done, right? What is it exactly? Well, this is trace and log events raised by user mode applications and kernel mode drivers. The API consists of 3 different components: controllers which start and stop sessions, providers which supply the events, and consumers which ingest the events, and there's these three other providers. In short, any Windows API call that you make can and will be logged. When we deliver malware into memory, there are three common API calls, well, for script kiddie stuff anyway, that we commonly make. Pop quiz, anybody know what those are? 1, virtual alloc, to allocate memory. Or if you're using NTDLL, it is NT-allocate virtual memory. 2, copy the shellcode using something like RTL copy or mem copy or something like that into that memory segment. Number 3, create a thread. Every time we do this, and there is an XDR or EDR running on the system, it sees that behavior from unbacked disk memory and it fires up a hook into the process and immediately collects all the event tracing and says, that's bad, and you're out of business, right? Kernel mode callbacks, it gets even more interesting. The Windows NT kernel allows a signed driver to register a callback routine, very, very commonly used by the AV, EDR, XDR industry. The high-level callbacks that are in use today are the create process notify, create thread notify, set load image, object register callbacks, and register callbacks. Does anybody remember the time when Windows Vista came out, and in those days, all of the defense vendors had hooked their telemetry by modifying the kernel. And Microsoft brought forward a thing called PatchGuard. And they said, you can't do that anymore, right? And all the vendors screamed and yelled, and they said, well, we need telemetry. What are you going to do? They said, okay, we're going to give you these things called kernel notification callbacks. And they give you the ability to get telemetry. And when you look at an EDR and XDR, you will often see them monitoring create process notify and create thread notify, and then using that as a trigger to inject into a process and determine what that process is doing. NTDLL API hooking. It's gone out of vogue a little bit these days, but what this involves is adding an opcode to the beginning of an API call. Let's say it's NT protect virtual memory, for example. And this opcode is just a jump instruction which jumps over to the XDR or EDR DLL that is basically notified of the use of that particular API call, and then it jumps right back to the NTDLL to complete the system call. Okay? Very commonly used up until a lot of the XDR and EDR vendors decided to move that functionality down into the kernel. But before they did that, they were hooking a lot of user processes in memory. And of course, I'm talking about Windows here, if that wasn't obvious, right? In fact, here's a pretty diagram that I tried to draw that gives you a bit of an idea of how these EDRs and XDRs actually work, all right? So number one, the malware uses an interesting API call like NT create process or NT create thread or something like that. Number two, there's a kernel notification callback that tells the EDR driver, hey guy, this process just used a create thread call. The kernel driver then says, all right, I'm going to inject a DLL into the malware process, which installs some NTDLL hooks and may also trigger a stack analysis and a memory scan to see what's going on. All right? So again, Microsoft's done a good job with this. Memory scanners being kind of the latest bogey that gets us, as well as stack trace analysis. Process tree analysis has been around for a long time. We monitor and track process relationships. We build an internal process tree structure. We look for anomalous relationships. We look for anomalous child behavior. And then we may even use an AI everybody fill out their bingo card. I said AI and ML, right? And yeah, to compare with known good behaviors, and then it may actually decide something is malware. Now, this is not quite as interesting because it's quite easy as a malware author to reparent a process to another process in the system and kind of break this analysis. Memory page scanning. This one's kind of interesting. Malware is typically going to allocate a virtual memory segment, like I said, and it's going to copy shellcode into that memory page. The machine code injected can be a full DLL, or it could be just a bunch of machine code that gets executed, right? A thread then is usually created resident in memory, okay? Now, here's the challenge. The EDR can use NT query information thread to determine the thread start address if that thread starting address is not backed by an image that has been loaded from disk. The EDR knows this is likely an injected thread and is malware, right? That's how this stuff works. There's a really easy way to get around it. You know how you get around it? You load a DLL into your process, and then you copy your malware over that DLL. It's memory backed now. Sweet. Disk backed, sorry. Call stack tracing and analysis. This one's interesting. Whenever a function call is called, the return address of that function call gets pushed to the stack. This is normal computer stuff. On return, it pops the address from the stack to populate the instruction pointer before continuing. And I'm mostly focusing on 64-bit here. So the stack pointer is the only thing that matters. The base pointer in 64-bit world is kind of ignored now, right? EDRs can use a kernel callback to trigger a call stack analysis. Now, they can trigger that based on all the things I kind of talked about already. Maybe an unusual API call, maybe a memory scanner. But as part of that, and this is more recently being implemented, they can unwind the stack and trace it back and check to see if any of the stack calls were made from an unbacked memory segment. And again, if they just come back from those function calls come from unbacked memory segments, they'll consider it malicious. Now, this takes more CPU cycles. It's a little more exhaustive, but it is doable. Related to this, in the PECOF file, there is a section called pdata. And the pdata section actually tracks function table entries for the exception handlers. And that can add supplementary information to this stack traceback mechanism, right? So in my malware, I just zero out that pdata section because that's something. I don't want to give them too much information. Now, this is going to get worse for us malware authors. First of all, from an offensive perspective, we can fake a call stack so it looks legitimate. And so when they go through this stack call tracing process, they draw a blank. Because they're like, oh, man, that totally looks like a legit call. And you're like, it totally is. Totes legit, right? And you're out of luck. The defense for this, though, is Windows 11 with kernel mode, hardware-enforced stack protection, whereby with the appropriate processor, the Windows kernel in 11 will maintain a shadow stack for every process thread that is running on the system, and it will compare that shadow stack with the real stack in memory, and the game is over. This is a significantly scary thing for malware authors because it's going to destroy things like RUP chains. It's going to destroy that call stack faking mechanism. This actually might be a real defense. Question? Is the hardware-enforced stack protection a real thing today? Yes. How widely is Windows 11 adopted? Questionable. How many organizations actually turn on the hardware-enforced stack protection? Probably negligible because there are older drivers which crash with a horrible blue screen of death because they do things they shouldn't be doing, basically. All right? Kernel driver block lists. Our world is full of vulnerable signed kernel drivers. This is awesome. Microsoft is now enforcing the kernel driver block list in Windows 11. This is also somewhat awesome. Why is it somewhat awesome? Because they cannot keep up. There are so many drivers out there that are not on the blocked list, yet they are still vulnerable. So malware authors, like some people I know that help me, will write code that uses a mechanism called BYOVD. Bring your own vulnerable driver. Once you have administrative access on the operating system, load your vulnerable driver. Once you have loaded your vulnerable driver, disable kernel callbacks. This is not a good thing, right? And this makes us vulnerable. Okay. Now, if you bring your own vulnerable driver, you have to be a good software author, because if you mess up code in the kernel, well, there is something called a bug check, which displays a blue screen, right? And it will happen. Turns out, I accidentally discovered that Microsoft writes drivers that do this inadvertently. That's no big surprise, right? All right, so all that was an introduction to say, holy crap, this malware dev shit just got real. In my line of business as the malware pit boss, I am now faced with making the software unique to continuously avoid any static analysis, squelch the event tracing, make any kernel callback notifications not interesting, or even better, turn them off, avoid getting our own NTDLL hooked and unhook it or not use NTDLL, make our process relationships not interesting, don't create a suspicious non-backed disk thread, evade all sandboxes, and don't use a driver on the block list. I'm exhausted just saying it. You can tell why this has turned into a full-time occupation. Now let's add in some requests, because my pen testers and red teamers, when I started producing stuff that was really interesting and useful, they wanted more. Hey, Joff, can you, give me .NET assemblies in both DLLs and XEs? Hey, Joff, can you give me native Windows XEs and DLLs? Well, MSI would be nice. Can you throw in some AppX, MSIX, and click once? Hey, dude, what about an XLL? How about a reflexive injection DLL? And on it goes, right? Where's all this going? It all pointed to me deciding we need to DevOps this process. We need to turn our malware production business into a CICD pipeline. And that pipeline, oops, I just broke the projection. That pipeline will have these responsibilities of performing code obfuscation, source code recompilation for unique artifact generation, dynamic encryption key generation, automated packaging for MSI click once and AppX packages, binary artifact signing, integration of third-party tools as needed. Oh, I'm getting out of breath. Dynamic regeneration of indirect kernel system call stubs, and continuous defense evolution. Just a small task, right? Well, it turns out this thing called GitLab in the Community Edition has a lovely CI/CD pipeline. It has all the lovely features that we need to do this, which is configured via a GitLab CI YAML file. The YAML file gives us different CI/CD stages. There's different jobs associated with this stage. Each stage. Pipeline can be run, triggered by a simple git commit or a push. and we can define trigger conditions to run the pipeline. And furthermore, for extra funsies, the pipeline can have dynamically created child pipelines. Cool. To do this, you have to install a GitLab runner on a standalone server or a virtual container somewhere, and the GitLab runner uses the GitLab API to register itself and service these pipeline runs. The runner processes the instructions in the YAML file, and in most cases will run a script indicated by the script tag. And so we decided, for platform independence reasons and diversity of malware demand, to deploy runners in Windows and Linux operating systems. In fact, this thing grew into a monster. This is what it looks like right now, and it's about to be scaled up. We've got a couple of Linux hosts running Docker, and we have a couple of bare metal Windows hosts. Well, they're not really. They're all in a single hypervisor, but we can think about them as just Windows operating system. And they're running the full Visual Studio stack and running commands in there such as Mage and MakeAppX and all those good things. The Docker servers, in the Linux case, have task-oriented Docker containers that check into the pipeline as individual runners. So I've got massive parallelism funneling back into the GitLab server with actually now I think 18 to 20 different runners ready to receive and compile software on demand. Okay? I turned into a DevOps guy. Whoops. So I've got this thing, we'll call it Zulu Foxtrot. That's not really what it's called. I have a custom malware framework that supports 3 different languages right now. It supports C#, Golang, and C and C++. It reads things called resource scripts, and it has additional features that allow us to do source code templating and obfuscation, binary artifact inflation, evasion modules in multiple languages to do things like patch and neuter, AMPC and ETW, and an integrated GitLab runner. And I fire this thing off on the Linux box and feed it, like the animal that it is, to compile on a per request basis from the pen testers a beautiful variety, a diverse variety of malware whenever they need it. Did I spoil these guys or what? So it kind of looks like this. We have sort of a preparatory step over here, the A0 pipeline YAML, and then it goes into a stage I call baking the malware. And this is as many malware frameworks that I need in that stage, and then it goes into a stage that consolidates the malware and then fires it off a bunch of child pipelines, which then perform things like creating click-once packages, MSIX AppX packages, and then it zips them all up, and then at the very end, it calculates a hash of every malware artifact, sticks it in a database, and then produces metrics on everything that was generated. I did this in a week. No, I'm just kidding. This is a 2-year project, okay? Zulu Foxtrot can parallelize its compilation jobs. So it's all feeding to Docker containers. It has mono MCS to compile the C#. It has MingW GCC to compile the C, and it has standard Golang installation to compile the Golang. And a lot of this stuff is pre-processed. Every time the framework runs, for example, if it involves putting shellcode into the malware sample, which invariably it does, the shellcode is encrypted with a dynamically generated encryption key every single time it runs. Meaning, what? There is no static artifact analysis you can do. All right? So, we're playing lots of games. We do things like obfuscate the source code, generate dynamic encryption keys, use very unique methods for the malware injection, such as avoiding the disk-backed thread issue by loading up an extra DLL and copying the shellcode over some legitimate memory segment. Maybe doing some thread context switches in there. All right? maybe even developing some very unique and proprietary techniques which I will not talk about. Okay? The whole thing is Python and YAML playing together. Okay? Now, I happen to teach an Introduction to Python course, so I know a little bit about Python. And if you need a really quick proof of concept script to actually manipulate YAML data, well, Python's an awesome thing to do that in. All right? So it makes it quicker to develop and quicker to deploy. The Python scripts that are called from the pipeline generate more CICD YAML file content, and then the YAML file artifacts get passed down from one stage to the next for further post-processing as needed, right? I just want to pause for a minute and say, if I can do this, what do you think the nation-state threat actors are doing? Probably something quite similar, and I would gamble on a much larger scale, right? So here's just a script example. This is a CICD pipeline script. It shows me with those different stages, and it shows me triggering it with a shellcode upload and then firing off some additional Python scripts down here, which generate these dynamic YAML to then go ahead and do more pipeline work, right? So it's sort of a cascading process that actually occurs here. All right? The dynamically triggered child pipeline is going to do, well, whatever I tell it to do. Maybe it's something to consolidate the malware into a single zip file. Maybe it generates an HTML manifest, and by the way, it does all those things, and then moves on down the pipeline, right? At present, the operators, or the red team folks usually, drive this through the GitLab, well, standard Git operations that you would as a developer, which is actually kind of suboptimal. They literally are dropping shellcode in a directory and pushing it, and the pipeline runs and generates all the magic, and they get out the other end like 40, 50, 100 samples of malware that they can then choose to run in any which way they want. Okay? I call it a YOLO git commit, which is, you know, git commit -a-m dot @ git push. Send it up for processing. The future plan, because this is suboptimal, is to create a web interface for configuration rather than having them tweak this YAML configuration file to turn on and off different dials and options that they might need. For example, if you take a binary artifact and inflate it by adding 100 megabytes of some single character on the end, what happens to the entropy of that artifact? It goes down, right? Also, most EDRs and XDRs and defense solutions, if they see a very large file with low entropy, they're like, nah, I'm not going to look at that. That's too hard. Move on, right? So there's plenty of things that can be done. We do have a configuration file associated with this, which we call buffet config. By the way, I call this thing the payload buffet. All you can eat, right? We do have an additional YAML file that has configuration options. So I just mentioned the inflation process, for example. And there are various options in this YAML file that folks can set. So I want to inflate this thing to 150 megabytes. And furthermore, just because we want to look legit, I want to fix the PE-CLOF checksum, recompute it, make sure that it's legit in the header, right? Those sorts of things. The expected results on a single pipeline run. 3 different zip files are typically produced today, containing all of the payloads and manifest information, and then any of the post-processing packages that we decide to produce. And right now that's click once, MSIX and AppX packages, right? Which is awesome. Has anybody in here heard of application manager domain sideloading? Yeah. Steve, you don't count, man. So I'm going to tell you a quick story. With application manager domain sideloading, basically what you're doing is forcing .NET to create a brand new application domain and then load an entry point into a .NET DLL or an assembly. And you can use a legitimate signed Microsoft binary to actually do this, which is, well, I would say suboptimal. So we dropped this on a few customers, and one of the guys, and he actually called me up at the time, he goes, Joff, you gotta see your malware work, dude. We're seeing this in real time. They're taking screenshots of the defenders trying to work out what's going on with this click once package, which has application manager domain sideloading going on. They uploaded the signed Microsoft binary to VirusTotal. Do you think that did them any good? What they didn't realize was that other little DLL sitting in there was actually where the malware is sitting. And, well, they just quarantined the box and kicked them off, but we were laughing so hard watching the guys upload. I know, everybody's hating me right now. I can feel it, right? But we were laughing so hard watching them struggle through uploading a legit Microsoft binary to VirusTotal and wondering why it was totes legit. All right. Let me talk about the return on investment for a minute. Any good organization eventually has management that says, hey, Joff, I know you're doing some wicked cool shit, but you need to prove it. So this is where metrics comes in, right? So this is why I created this hash database that actually captures a hash of all the artifacts and allows me to measure the number of artifacts produced, and additionally has the side benefit that with those hashes, we can actually play API key games with things like VirusTotal to see if our malware has been uploaded to different places, right? But we can also count the kinds of things we're producing using a little bit of hacky Python code and some basic data analytics. I didn't know I was going to be that guy either, but turns out that I am, okay? So this is just a picture over, I don't know, what is it, 8 days of various uses of this pipeline mechanism and broken down by the different kinds of artifacts that are being produced on each run of the pipeline. And then I did an informal poll of the penetration testers. And by informal, the ones that are sitting in here can certainly attest, it was literally in teams. I said, how many hours do you think it saves you to use this production malware pipeline? And most of the testers converged on the idea that it saved them between 8 and 16 hours per customer engagement. So very rough table napkin math here. If we in 8 days have generated 1,652 artifacts and it saves the tester between 8 and 16 hours per engagement using a single artifact, well, let's just get crazy and imagine they used 2 artifacts. Over this time period, we've saved between 224 and 448 hours of time. I think I'm paying for myself pretty well, okay? It's working. All right. The advantages, I think I need to wrap up soon. The advantages of CICD is we have these unique artifacts that are produced on every single pipeline run. We have a large diversity of payload options. We have all these unique encryption keys for different aspects of binary artifacts. We have unique shellcode encryption for each one of them. We have unique source code obfuscation for any source code that can be reversed, such as C#, for example. We have unique assembly machine code encryption. We have flexibility to implement different techniques quickly, and we can easily add new post-payload processing steps as needed. And as I've already said, the static analysis of binary artifacts becomes very difficult. I am an APT. Here's the disadvantages. You knew that there was a downside to this, right? The disadvantages are there are multiple dependencies. Imagine you are building a Docker container that's trying to run 3 different compilers and obfuscate source code and encrypt shell code, and you've got duct tape and baling wire Python scripts holding it all together and all this back-end infrastructure to maintain. Versioning becomes very interesting. The speed of execution of the pipeline and troubleshooting that is also kind of time intensive. If you've got an error somewhere in the middle of that DevOps pipeline, you have to run it again and wait the 3 to 10 minutes. By the way, I think that's pretty darn good. If I'm producing several hundred malware artifacts in 10 minutes, I'm pretty proud of that. But nonetheless, the troubleshooting takes a little bit of time. It is highly sensitive to configuration mistakes. Steve over there, love you, man, decided, hey, I love your buffet config, but, I want to change the case of a few options. I was like, Steve, don't do that, man. It's going to break, right? And, well, he found out that it broke. So it's a little bit delicate from time to time. And by the way, Steve is one of these fabulous red teamers. He can just walk up to a computer and it falls over dead, right? Just the way it happens. That's it. Just proximity, right? There's also a bit of an operator overwhelm factor. Hey, Joff, I just got 300 or 400 artifacts. What's the next question that's going to come at me? Which one do I use? I was like, I don't know. What do you need to do? So we're kind of working on that problem. I think what's going to go on next is we're going to build in profiling for specific endpoint product evasion so that we can put a bit of context around that question. Now, before you think I'm totally evil, we are a penetration testing company that is tasked with performing appropriate adversary emulation. This is exactly that. Malware initial access operations has to be solid nation state level to give us appropriate adversary emulation. It is required, right? Even though many of the defense companies probably do have me listed as an APT, right? I recently polled one of our pen testers, how many hours? No, I already spoke to this slide, right? This was the 8 to 16 hours. But we found some other interesting results out of this exercise, and that is this. Not everybody is built equal, duh. Some pen testers are just starting their career. Some pen testers have great dev skills and were kind of envious and going, I want to join Joff's team, man, he's doing cool stuff. Some pen testers could care less. I love what you do, Joff. Do more. Right? Awesome. But, even Steve, who's a very talented guy, I'm sorry, Steve, I'm picking on you too much, but he's a very talented guy. When I asked him this question, he said a couple of things. He said, dude, why are you even asking? Your work is invaluable. He says, I would have to, and I'm paraphrasing, I would have to spend 2 days fumbling around the internet looking for proof of concept code to paste together an attack, and now I can just press a button. And that's really the essence of it. The other thing we found is our penetration testers have made the comment to me that your work has changed the way I operate. I don't have to focus on producing those artifacts. I now focus on my op itself. I focus on the techniques I need to use to do the rest of the gig instead of all that creation front end, which is incredibly valuable. It changes the way everybody has to think. They don't have to worry about this aspect, right? It's done for them until it breaks. Well, and occasionally it does. The other thing that happens, and I will tell you this, is the more talented testers now will go out and find a new technique, and instead of trying to implement it themselves, they are literally just sending it to me, and saying, Joff, we'd like to see this one done. So to me, that is a huge compliment, and also says, I have succeeded in creating the malware pit boss operation, right? Whole bunch of references here if you're interested. This is far from an exhausting list. There's so many things here. But when you're developing malware, WinDebug, for example, System Informer, SysInternal's Process Explorer, API Monitor, Visual Studio, Mono, MingW, Python for quick and dirty POCs, PE-Civ to examine a running artifact to see if it detects whether it's got a hook in it or any shellcode, DN-Spy for assembly, reversing, Resource Hacker is also very useful. If you want to take a picture of the slide, you are totally free to do that. Of course, I think this is being recorded as well. Okay. .NET obfuscation. I use a custom source code templating system myself. I am not releasing that, but there are many other .NET source code obfuscation tools out there. We have things like Confuser EX, Codeception, Obfuscar, and yet another obfuscator. There's tons of these projects out there if you want to obfuscate .NET source code. Now, it's useful because .NET feeds right into the MSIX, Apex, and Click Once world. Right? So we sort of keep that in our sights. NetClone, adaptive DLL hijacking, a shout out to those guys. Native Windows DLL sideloading is something that is a useful technique. This is the Microsoft Teams still has a vulnerability that allows you to sideload a DLL. What? So, of course, the guys came to me and say, Joff, we need that in the pipeline. I was like, absolutely, 100%, let's do it. All right. SysWhispers 3, if you want to make indirect to kernel calls, avoiding the anti-DLL calls. That is changing a little bit lately, mostly because of call stack analysis and memory scanners. Indirect syscalls to the kernel are less necessary, I guess, or less evasive. They're not quite as in focus, I guess would be the word. But anyway, that's built into the pipeline for the C-based pipeline runs, and it actually generates a dynamic egg hunter for evaluating the syscalls. It fits into the CICD pipeline just wonderfully, right? So by implementing, I'm trying to wrap up, CICD, we saved all this valuable operator time. We bring malware to a wider group of pen testers. We gain all this flexibility. We increase the consistency of the pen testers' actual MO, if you like, right? Increasing that ability to get more samples into more hands for use. We provide a consistent platform for further malware development. And we provide a platform to integrate new malware generation frameworks. And we keep providing sporting fun in the offensive and defensive arms race, which it most certainly is. Lots more resources if you're interested. Another picture slide there. A bunch of blogs that I was tinkering around with recently that I think are more relevant, especially around the call stack spoofing and digging into Windows architecture. You would not believe how much time I have spent in a Windows debugger, essentially manually going through machine code looking for opportunities, right? A lot of time. And that's all I've got for you. Now, look, this was a drinking from the fire hose kind of talk, encapsulating basically 2 years of work into one massive overview. So I'm not expecting there are too many questions, but I'm certainly willing to take anybody who has a question. So,
if there's any questions in the audience, we'll bring a microphone to you if you can just hold on. Raise your hand.
All right, now I'll do a shameless plug. Somewhere between myself and maybe Steve over there, Steve's been a feature of my talk now, we will be revamping and developing a malware development techniques class for anti-siphon. And so that's a little teaser. So if this interests you greatly, Steve already has a course. I have an older one that needs revamped. Stay tuned. We will bring some more techniques and interest forward for you in the form of an anti-siphon course, okay? Thanks for coming, everybody. It's been great.